Hello everyone, my name is Luciano Combi. I'm a graduate student at the Argentine Institute of Radioastronomy, and I'm working with Manuel Campanelli and collaborators at the Rochester Institute of Technology. So today, I would like to show you some of our recent results on GR-MHD simulations of supermassive binary black hole systems with spin. So let me start with a little bit of context here. So a supermassive binary black hole forms after two galaxies merge. So the binary system will be surrounded by the gas of the galaxy. And contrary to stellar mass black holes, at least most of them, this means that the system will emit gravitational waves and electromagnetic waves. So this is a very interesting multi-messenger source. And depending on the type of system, the specific parameters of the system, there are several different strategies that we can take to make models and analyze this type of systems. So one of the things that we have to consider is that the system is highly nonlinear. We have the time-dependent spacetime coupled with the MHD fluid and all the turbulence of the accretion. So most aspects of the system must be studied with numerical simulations. If we consider a binary system at close separation in particular, we also have to take into account general relativity. So in principle, we will have to solve Einstein's equations coupled with the MHD fluid equations. And for several reasons, this is computationally very expensive. And so we usually use approximated methods to tackle the problem. For instance, if we consider that the binary is in the spiral regime, so it's emitting gravitational waves, but it's not too close to merger, we could approximate the metric of the spacetime using some analytical approximation, and then we can evolve and focus our computational resources on the fluid. And this is what we do in our work. So essentially, I want to show three different results. So in the first work, we built an approximated metric of a spinning binary black hole spacetime. So the new thing is that we built a computationally efficient way to represent spinning black holes. And then we use this metric to evolve the MHD equation and analyze a circumbinary disk for a long time in full MHD, but excising the inner part of the cavity. And in the last part, we analyze how is the accretion of the mini disk that form around each black hole, and once we include the spin, what happened with the mini disk if the system emit jets, and what's the difference between spinning and non-spinning systems. And also let me advertise Eduardo Gutierrez's talk. He will be talking about ray tracing of the simulations I will present here. And it's our very exciting results. So let me start with the first part. So as I said, instead of solving Einstein's equations, we built an approximated metric to describe a spinning binary black hole. And we do this by superposing two black hole terms in harmonic coordinates. And we implement a particular boost. So these two black holes are moving and in spiral orbit. We use post-Newtonian trajectories to describe this boost. And the important thing is that this metric is valid in every point in space, even near and inside the black hole horizon. But since the metric uses the post-Newtonian trajectories, the metric is only valid in the spiral regime. So in the first work, we tested this metric. We saw that it's a good approximation of Einstein's equations. And then we take this metric and we put it on an MHD finite volume code. We use HARM 3D. And we analyze how is the circumbinary disk accretion into a binary black hole when the black holes have spin. And so in this work, led by Federico Lopez Armengol, we found some usual characteristics of the system found in other works. For instance, and most importantly, in this equal mass binary black hole, once you consider the MHD and the full 3D, you have a very coherent structure orbiting the inner edge of the black hole. This overdensity that we call the lump modulates the accretion into the cavity. And so we found that essentially after evolving for a very long time, unprecedented times in this type of MHD equations, we found that for spinning black holes of 0.9 and aligned and anti-aligned, the accretion is slightly changed into the cavity because the frame dragging of the spin changes the dynamics of the streams that fall into the cavity. But we also proved that once you include spin, the bulk properties of the circumbinary are not affected by spin. So then we continue some of the work that Bowen et al. Started in 2018, where now you don't excise the inner cavity, you include the black holes into the evolution domain. And the new thing here is that we include this new spacetime that have spin. So we use a snapshot of a previous simulation. So we have an evolved circumbinary disk, and then we let the system evolve in this realistic initial data. And essentially what we find here is that mini disks share the same quasi-periodic behavior as the non-spinning binary black hole. But once you include spin, the mini disk are more massive by a factor of 2. So this is expected because the spinning black holes have a smaller ISCO, and so this allows more material to orbit the black hole closer to the horizon, and so the mini disk is heavier. And so we also analyzed in detail how is the accretion rate into the black holes, and we found actually that the accretion is very similar between non-spinning and spinning black holes. So this indicates that there is a shared mechanism of accretion into both cases that dominates the system, and this mechanism is given by the lump. So we analyze this in detail. So here you see in the upper panel we have spinning black holes, and in the lower panel we have non-spinning black hole. So you can see here that you have a disk structure, and on top of that you have this one arm given by this lump that comes from the inner edge of the circumbinary disk. So most of the accretion occurs here through the lump, even if you have a more disky structure. And well, we also analyze how is the angular momentum of the material that surrounds the spinning and non-spinning black hole. So for the spinning case, we saw that, of course, as expected, you have more material with higher angular momentum with respect to the ISCO. But as the system shrinks and spiral, the two quantities, meaning the quantity that plunges in directly and the material that orbits the black hole, are comparable. So at some point, what we notice here is that the accretion that occurs directly into the black hole given by the lump is very important and a very notable feature of this equal mass binary black hole. Another thing, of course, is that since we have spin now, we have an ergosphere, and that helps extract energy through a Poynting flux from the system. And we saw here the appearance of a jet-like structure. These are the magnetic field lines, and we see here funnel and a very shaky structure because this is density following the black hole. So you can see that the movement of the black hole orbiting around the center of mass is really affecting the stability of jet. And so we also proved that in the spinning case, this is the Poynting flux, again, a meridional cut of the Poynting flux. You see here a more prominent structure, while the non-spinning is more uniform and without a preferential direction. And another important thing that we saw here is that the efficiency, that is the luminosity over the accretion rate into the hole, is close to 10% for the spinning case. This is for each black hole, like a sphere following each black hole, and the dashed lines are the non-spinning case. So you can see that there's almost an order of magnitude from spinning and non-spinning. And the interesting feature here is that you have this periodicity and of the Poynting flux that is correlated with the periodicity of the accretion rate. So these two quantities are, of course, connected in the time domain. So this is an interesting signature for future observations. And so let me conclude here. What we've done is we built an approximated spacetime representing binary black holes with a spin in the spiral regime. So this allows us to evolve the emission equations in an efficient way and study for the first time realistic scenarios where we couple a realistic circumbinary disk evolve with what happens inside the cavity and how are the mini disks that form there. And so we also saw that the lump dominates the accretion, and we also saw that in the spinning case we have a modulated Poynting flux that is shares the same variabilities of the accretion rate. So in our future work, we expect to do some of the ray tracing of the simulations and so obtain realistic light curves. And also we hope to incorporate more detailed radiation models and explore the parameter space, because this is only for equal mass and low values of spin. So there's much work to be done in this sense. This is essentially all I wanted to say. So